let us do a few more of the MCQs. Toughness of a material can be measured or approximated through which testing? Tensile testing, impact testing, fracture toughness testing, or all three? You know, after tensile testing, you get the stress-strain graph, and the area under the whole graph from the beginning till fracture is a rough value of the fracture toughness of the material. Impact testing, of course, you find the impact toughness of a material, so it is toughness testing. An actual fracture toughness test with the compact test specimen is also the fracture toughness. So either measured or approximately measured, so means all three is the correct answer, right? Mode 1 testing for plane strain fracture toughness refers to dash mode of a specimen and load orientation. Opening or tensile mode, sliding mode, tearing mode, any of these. This is definitely wrong. We know that mode 1, mode 2, mode 3 are seriously different. So any of these is not the right answer. Sliding is mode 2, tearing is mode 3, opening or tensile is mode 1, right? The load is in this direction, the crack is in this direction. So this is the crack surface and the load is at 90 degrees or perpendicular to it, and it is a tensile load. So when this tensile load is applied, the crack starts to open. So this is called opening mode or tensile mode, right? So these were some of the MCQs. Of course here, just for my ease, maybe you noticed, maybe you did not, that in each of these MCQs that I just discussed with you, I had written number 1 as the correct answer. But when you receive it, they will be shuffled and they will be anywhere. First may be correct, second may be correct, third may be correct, and so on. Okay? And of course, I have discussed only a few. I don't have enough time to discuss all the possible MCQs from chapters 1A and 1B. But of course, during the exams and so on, you have access to your lecture notes and to your book. So if you study my lectures carefully, then you will have no problem, inshallah. The second question, a TV show offers you the chance to earn $50,000 by simply hanging from a rope for just 1 minute. The rope is attached to a sheet of glass, which is 300 centimeter long by 10 centimeter wide and 0.12 centimeter thick. The glass sheet contains a central crack with a length of 1.62 centimeter that is oriented parallel to the ground and perpendicular to the lowest side of the glass sheet. The fracture toughness of the glass is known to be 0.83 megapascal root meter. The rope is suspended over a deep hole containing quite dangerous green mamba snakes. Geometry factor including finite size correction is given by this equation, where of course A is the crack size and W is the width of the plate. Assuming that your weight is 60 kilogram, would you try for the big prize of $50,000? Use a simple sketch, give reasons for your answer. So as I always tell you, read the question carefully, read it again, take down the known data, and then what is the unknown? Of course, because it is the beginning of the course, the only equation is K1 is equal to sigma root pi A. There is nothing else, right? So you do that, but take your time. You have already solved it, so I will directly now go into the solution. So, right, what is the geometry? Make a sketch. The sheet of glass is 300 centimeter by 10 centimeter by 1.2 centimeter thick. So thickness is of course in the thickness direction, length and width, right? So of course I have drawn this, length is length and width is width. Now it contains a central crack with a length of 1.62 centimeter. If it is a central crack, if it is a central crack, the length is 2a. So this 2a is 1.62 centimeter, which is oriented parallel to the ground. This is oriented parallel to the ground and perpendicular to the longest side. So this is of course the longest side. This is the length, this is the width. So it means that this is 300 centimeter and this width is 10 centimeter. And this is a central crack. So this is the very simple thing. And then because right, you are hanging from this and so on. So that is the vertical tensile load. So this is the simple sketch. If the sketch is there, then you know exactly the orientation and the size of the crack and so on. So you have solved it. So there, I mean, your solution most probably would have been correct. You are all intelligent people and this was not a very difficult question to ask. But let me see. So I tell you always that once you have done all the knowns and unknowns, you know which equation. So there is only one equation, k is equal to k1 is equal to y sigma root pi a, right? Now this y is the geometry factor. So this time there is an equation given for the geometry factor where a is the half crack length, total crack length is 2a and w is the width. So here, because 2a is 16.2 millimeter, I will convert everything into millimeter. Therefore, a is half of that, 8.1 millimeter, and width is 10 centimeter, which is 100 millimeter. So therefore, you put the values. I am saying that y is equal to 1.0196, but you do whatever calculation and maybe this answer is right, maybe this is slightly different. Okay. Now, stress is force upon area, of course, where F is the load and A is the cross-sectional area. Now, your weight is given as 60 kilogram, but please don't take kilogram as the weight, multiplied by 9.81 so that you get the weight. 60 kilogram multiplied by 9.81, this is your weight. And the area is how much on which it is acting, right? 100 is what? 100 was the length and 1.27 was what? It was, right, 100 is the width, sorry, not the length. 100 was the width, length was 300. So this width multiplied by the thickness, right? So that will be the cross-sectional area on which the sigma is acting, right? You have a plate like this, and there is a load which is perpendicular. So this side and the thickness side, this side and the thickness. So this side is this 10 centimeter or 100 millimeter and the thickness is 1.27. So you find sigma, right? So sigma is say 4.63 megapascal or whatever it comes out to be. So now you put those in the equation, right? Put those into the equation. Y value you put y, right? For sigma you put this 4.63 megapascal. Root pi into a. A is the given crack size. So you have found the K1 value. Now this comes out to be 0.75 megapascal. 0.75 megapascal. If the given K1C, fracture toughness of the material, is 0.83 megapascal, then the stress intensity under your condition, is less than the K1C. So you are safe. If the stress intensity under these conditions is equal to or more than the K1C, then of course there will be catastrophic failure. So, right. So you get the answer K1 according to all the data as 0.75, and this 0.75 is less than the K1C given. We could do the other thing. We can solve the same problem in a different way. We use the K1C value. In this equation, we use the K. Y, of course, we have calculated. We use the K1C value, right? And the given crack size. And see that what will be the sigma at which it will fail. Do you understand? If this is K1C, this is Y, and this is the given A, then from this equation, if you separate out sigma, then that will be the sigma critical. That under these conditions with K1C, the material property, at which sigma it will fail. So you find out sigma from here and you find out the actual sigma. If this sigma is less than the sigma critical, you are safe, right? So you can solve, many times you can solve the same problem in more than one way. So from this same equation, either use K1C as the material property and find the sigma C or sigma F at which the material will fail, and then compare your actual sigma with this sigma F. If your actual sigma is less than that, you are okay. Or find the sigma, put these values here, and find the stress intensity K1 in the current situation, and then compare this K1 with the given K1C, right? So this is it. So you have solved it, you have done it. If you use all the correct units and so on, then you will be safe. Don't mix them up. Don't do 1 millimeter, 1 centimeter, 1 meter, right? All millimeters, all centimeters, all meters, and so on. Now, with this answer, the problem is that this is 0.75, this is 0.83. So there is very little margin of safety. It is safe, but if anything goes wrong, if the material property is not 100% correct, if the glass is not uniform everywhere, it may fail somewhere else. So if you are feeling brave, you might try for the money. In general terms, the margin of safety is somewhat low. It might be better to let a younger and lighter sibling earn the money. Sibling is your brother or sister. Your weight was 60 kilogram. If somebody has a weight of 50 or 55 kilogram, then maybe the factor of safety would be better. So this comment is very important, that this is the answer and you can say, yes, it is safe. I will go for the $50,000. But the thing is that, you see, it is very close to the critical point. So it is not really safe. Therefore, if you are given the choice, you will say, no, please, my life is much more important. I don't want to risk my life based on, but if my weight is lower, 55 kilogram or 50 kilogram, I'll do the calculation, and then maybe this comes out to be only 0.6 and this is 0.83, then I have like 30-40% factor of safety. So then I'll say, okay, now I'll do it. Okay, so this was your quiz, and most probably all of you would feel very happy today looking at this solution if you got the answer totally right. And you will see later on, if sometimes I share that, you see, I give a -0.5 here, a -1 there. I am very particular about the units that you use. I want you to be sure that you are using the units correctly as engineers should do, and your assumptions and so on are right, your sketch is correct. So there will be points for all of the things, and maybe you get a 10 out of 10, maybe you get a 9 or an 8 and so on. And of course, when you look at your mistakes and so forth, you can learn from there. And I will, as soon as I finish the grading, I have been very busy, and grading nowadays is very tough because you have to download all your solutions, the PDF solutions and so forth, and then start grading. And I am teaching 2 different courses. If it was 2 classes, 2 sections of the same course, but I am teaching, so you make 2 different lectures all the time, you make 2 different quizzes, 2 different solutions. So it will take a little time, but as soon as I have graded it, then I will send you an email, right? We will share that with you. So now let us get back to the actual lecture that we were supposed to do today. So I am starting that, you see, you have the Paris-Urdugan law, the dA/dN is equal to A delta K raised to M, or as I have shown you in some other books, capital C here, a small n here, it is still the same thing. If you want to linearize it, you take log of this side, log of this side, so that linearization thing is there. So this is the basis of fatigue life calculations. I mean, how we will go to do fatigue life calculations later on.